So yeah, so the way I'd like to run this usually is to basically jot down stuff that you guys were reading in the paper and that you didn't quite understand, or if there's any terms or words or concepts that we really should cover, and then we'll go through the actual paper little bit by little bit, so that I don't know that we'll get to the whole paper in an hour because it's actually a pretty dense paper. But I liked it because it has so many good concepts in it that if you don't understand most of the concepts in this paper, then it's hard to move on to more advanced papers. And I didn't want to throw like crazy statistics at anybody. There's nothing crazy really in this paper. It's just a dense paper. So let's start with any concepts that you might want to cover, or any words or terms in the paper that you're like, I don't know what this means. Or I learned this at one point and I have no idea what I actually learned back then.
I got two on that, Brian.
Okay.
Go for it.
Okay, so I'm pulling up the paper full screen so I can't see you guys.
No worries.
Okay, so I'm looking right now at I believe it was the statistics portion of it.
Okay.
Statistical analysis. And one of the points were, it says skewness and kurtosis indices were accounted for.
Okay.
And I had no idea what that was.
Okay. All right.
And I'm trying to see where it exactly was.
Oh, I know what you're talking about because I highlighted that.
It's data analysis. It's 1, 2, 3, 4 lines in.
Okay, yeah. Allison had that too.
Okay.
Yeah.
And I do too. I just didn't read it very well.
As far as z-scores, I'm familiar with them, but that's a very, very basic familiar. Like, hi, how you doing? How's the wife? I haven't talked to you in 5 years.
Sure.
So if we can get just a quick refresher on z-scores, just so I know how to start dividing the ratios for acute to chronic.
Absolutely.
I had a question. I'm not sure if this is too early for it, but when they started going through the statistics of their season, one of them, they said 38% of their population was used in both seasons. 62% was either in one season or another. So I want to know like how that confounds everything. Like, or like, is that a red flag for you when you see something like that? Like, what's a good amount if there is any?
Where's that at, Tony?
So I believe it's one of the first paragraphs. Let me see if I can drop that in for you. So methods and participants. It says of the two seasons, 38% participants competed in both seasons, and 62% participants completed in one season, equating to a total of 73 individual seasons of rugby league. And then went through the 13-week preseason period and the distance that they went through.
Okay.
I would also like to see the accuracy of the GPS data, if that is a factor in this, which I feel like it could be.
What about the accuracy you said?
Like any like catapults being used, but if you're using it in a covered stadium, or if the sensors aren't aligned, but there is a margin of error. I want to know like how they accounted for that, or maybe I just kind of skipped over it, or if they even mentioned any of that. Besides that, they used binary logistics regression model.
Okay. All right. Binary logistic regression model. Okay.
And the last one is, how does Brian Chung get his arm so big? And I want that added.
Dedicated arm workouts twice a week.
Lance and I did 30 minutes of biceps.
And they're still not that big.
They're 30 minutes overall, right?
Yeah.
That's it. That's all.
Okay, so that's it for me right now, at least.
Okay. Lance, do you or Allison have anything to add that you guys thought you wanted to clarify? Like, you're just reading it, you're going, I have no idea what this means.
So I missed the skewness and kurtosis indices. I would like a refresher on that.
Mm-hmm.
So +1.
Okay.
The I'm curious to hear what Tony is wondering about the GPS validity. It seemed like they addressed it, but I don't know how well they addressed it. I'd be curious to hear your perception of that based on the article they referenced. Definitely +1 on binary logistic regression model.
Yep.
It says null hypothesis testing was conducted using a binary logistic regression model.
Right.
With injury/no injury as a dependent variable. So all of those terms would be really helpful to go through.
Okay.
And then the relative risk times divide 90% confidence interval. I don't know what any of that means. And they went back through that a lot. So that was
sorry. Can you repeat that? Sorry.
Yeah. The right under in the statistical analysis section, they say, relative risk times/divide 90% CI were calculated.
Oh, okay. Right.
So I didn't know what times/divide even stood for.
Yeah, that's fine.
I think that's all I had.
Okay. All right. That's a good start. I like that. Oh, we don't need that. Okay. So I think where I generally start when I start reading a paper, I do start by skimming the introduction. I don't read it in a lot of detail because there's nothing usually that important there. It sort of sets the stage for what it is that they are trying to do. And so the reason why I read the introduction is not because I want to find out what they want to do, because that comes later, is I want to find out how they express how they want to, I want to see how they express their goals for this paper. Because it's not unusual to read somebody's goals for a paper in the introduction, read the paper and realize that those two things are not the same thing. Okay. So it's nice to know what the authors think they're doing. And then when you go through the paper, you then kind of are like, well, did they actually do what they said they were going to do? Because sometimes it happens more often than not. Well, no, not more often than not, but it happens a lot where it's not. So in the introduction itself, it seemed like it was pretty okay. Where I hung up on the most was their definition of injury, because I feel like in rugby, there's kind of two different kinds of injury. And so if you're talking about injury prevention, there's not really a good definition of that. And maybe they'll get into that in the methods. And that's something that, as soon as I read the introduction, I automatically wrote down that this sort of define what injury are they defining here, right? So, can you prevent somebody from colliding into another player? I don't know that you can necessarily. You might be able to control reaction time, but in the grand scheme of things, there's stuff that goes down in rugby where I'm pretty sure nobody has any control over it, yeah. Right? And so, acute versus chronic workload, that's gonna be an issue if they're not differentiating those kinds of incidents. If it's just general trauma, then you're gonna have a mix. You have this mixed problem of the stuff that you can control versus the stuff that you can't control, right? And that's the first one that really pops out at me.
Brian, real quick.
Yes.
Is with your issue, just so I'm making sure I'm on the same page as you, is your issue the fact that they didn't define it in the paper, you couldn't see it, or the fact that they didn't put it in the introduction?
It's just, for me, when I'm just going through the paper and thinking to myself, okay, so this is something that I want to look out for when I start reading the rest of this paper.
Okay.
Right? Okay. Because if it's not there, then, and this has to do with knowing what it is that you're studying. If you know nothing about rugby, then you probably aren't going to be, you probably don't, that's probably not a red flag. But if you know something about rugby, then when you read it, you're like, oh, there's a problem there. Because if they don't account for weird, the sort of random injuries that happen versus stuff that we could, where an acute or a high chronic load / ratio or whatever you want to call it, you know, might account for the fact that somebody is injured. Well, then, you know, are they actually doing what they say they're doing? How much of this final result is going to be affected by the fact that you have this blend of preventable and non-preventable issues?
Okay.
Right. Gotcha. All right. So the next thing that I have highlighted here is a very basic statistic, right? So it's a mean and a standard deviation. Do you guys understand means and standard deviations?
2 thumbs up over here.
Okay. So I don't need to go over that. Perfect. All right. I don't make any assumptions. All right. So they do define injury, which is good. And so they actually include acute and overuse injuries. But they don't actually, like, there's not really a differentiation between stuff that they think that is preventable versus stuff that isn't preventable, right? So this is automatically going to be a little ding on this paper, because the injury is defined as any time loss injury that basically results in the player being unable to complete full training or missing match time, right? So they are going to define them as acute versus overuse, but, you know, how much of the cause, the sort of the cause and effect that they're trying to get at is really attributable to training load, right? So if you catch a ball slightly wrong, how much of that, and you break your finger, right? That happens in rugby a fair amount, or you sprain your finger, right? How much of that is attributable to your actual training and your, you know, like acute workload versus chronic workload is really about fatigue in some general sense, right? So, you know, how much of that is really is fatigue related versus not? Hard to say. The way that they've done it does allow them to capture everything, which is kind of nice, but then it's going to be difficult later on, especially as we get through the rest of this paper. Okay. Data analysis. So let's go into the data analysis and let's go into some of these questions here. What did I say? Oh, right. So I highlight skewness and kurtosis as well, because they don't actually tell us so my comment is skewness and kurtosis of what? Right? So there are these things called skewness and kurtosis indices, which are basically numbers that tell you whether your sample size, not your sample size, whether the distribution of your samples are skewed versus kurtotic. And I'll talk about what those mean in a second. But they don't actually tell us what measurements they actually use those indices on. So not knowing what those were, it doesn't really give us a lot of information, even in the results section where they may say that it's fine, right? Because fine is not, like, there's no such thing as a straight cutoff of what is an acceptable skew or an acceptable kurtosis. Like, it's kind of, in some ways, you don't even bother. Like, I don't know why they bothered in some ways, because there's not really a good rule for when skew is skew and when kurtosis is too kurtotic. So let's talk about that right now. Where did I go? CM1. All right. So skewness and kurtosis. How do I get a new page here? Oh, there we go. Okay. Done. All right. So, skewness. So if you understand means and standard deviations, then that means you understand what a normal distribution is, because that is basically what a mean and a standard deviation is a summary statistic of, right? So if you have a non-normally distributed population, calculating a mean and a standard deviation has no meaning, because it doesn't allow you to derive any information out of there. So a normal distribution, you know, we're all pretty familiar with this bell curve, right? Roughly, that's not a true bell curve. But, you know, the characteristics of a normal distribution, right, are that your mean is in the middle. So both your mean, your median, and your mode are the same, right? So they're all equal to each other. I probably could have done that in a better way, all right? And your standard deviation is a measure of your variance, right? And in a normal distribution, 66% of your data lies within one standard deviation. And almost 95 to 96%, we'll say 96%, lies within 2 standard deviations of your data. All right. So if your population doesn't fit this criteria, when you do your statistics and you calculate it and you look at your curve and you're like, oh, this doesn't work because, you know, only 40 to 5% of my population fits within 1 standard deviation, then you don't have a normally distributed population. Okay. If your mean, your median, and your mode aren't almost the same or not the same, then you probably don't have a normal population, right? So what is skew? So skew is when basically this curve shifts in one direction or the other. So, so a skewed distribution could look like this, or it could look like this, right? So, sorry, that's a really bad. Let's do this differently. Let's do that. Okay. We'll center it all on the same, right? So if that's your theoretical midpoint, then a skew would look more like this, or it might look like this, right? Where the peak of your sample is not in the middle of your distribution. Okay, so if these are all the if these were values from 0 to 100, and this is value 50, roughly, right? Now your peak is not in the middle. So okay. That's what skew refers to. So that means your values like I'm waving my pencil over the screen thinking you can see my pencil. It's awesome. Yeah, I'm just waving it over, just like roughly circling, and you like nobody can see what I'm talking about. So in this one here, right, all your values are sitting around 25. So this is technically this is a skewed low, right? And in this one, maybe all your values are sitting around 75, so it's skewed high. But there's a bias in these two, in both of these samples, either to the low end of the values or to the high end of the values. All right. And your midpoint here doesn't correspond to the peak of your frequency of your sample, right? Does that make sense?
For the most part, can I ask a question to clarify?
Yes.
So the 25 you just drew.
Yes.
In that skewed low graph, if I'm correct, wouldn't your mean would be around the number 50 and your median would be around the number 25, correct?
Not necessarily. It really depends on what's on this axis here, right? So you can have you could have, let's I'll just erase. That's easier. Just take this one out here. So what you could have is a really effed up skew where this happens.
Is that the technical term?
Oh, totally. Yeah.
Right.
So you could have a skew that does this. Okay. So, you know, if you think about, if this is frequency, right? And then this is your values. And this is, say, 50, right? So in this case here, your peak is here. Let's change the color. And so this area here, this frequency here, the area under the curve is the actual number of people that exist from this value and lower, right? And then all of these people here are your value and higher. So you don't necessarily, your mean might be, your inappropriate mean, because you shouldn't calculate a mean off of this. This is a great example of when not to calculate a mean, right? So if you calculated a mean off of this, it would probably be somewhere around here, right? It's going to be close to the peak, but you have to sort of account for the fact that the volume is distributed quite a bit, right? If you calculated a median off of this, it might end up somewhere, over here, or even over here, right? Because you sort of have to think, well, how much of the magenta area it's definitely more than 50% of the total volume under this curve.
Yeah.
Right? And the median is the 50% value. It's the value where half of your values are higher and half of your values are lower, right? So your median might not be anywhere close to 50. It's just that 50 is roughly sort of the midpoint. And it's sort of what would be if you had if all of your values went from 0 to 100, like all the possible values, if your range was 0 to 100, then you would have an even distribution of people on either side of 50 if it was normal.
Correct. I got you.
Right?
Yeah.
But because you're not normal, you don't have an even distribution on either side of 50.
Yeah.
Right? And most of your values are biased towards the low end. So skewness is interpreted within the context of what your possible range is. It's not an arbitrary, it doesn't make a lot of sense arbitrarily, because it really depends on the range of possible values. So if we're measuring body temperature, for instance, right? Let's say body temperature in people who don't have a fever and who are sitting at room temperature, not doing any exercise, right? That is going to be a really narrow number of possible values, right? So, I can't remember what it is in Fahrenheit, so I'm sorry. But, in terms of Celsius, it's going to range between like 36 to maybe 38 point something. You're not going to have any other values. Like if you have values outside of that, then something's wrong with that person, right? So, that's going to be where you sit. And if you have a normally distributed population of temperature in those people, then those are going to sit roughly centered around the middle of that zone, right? But if it's skewed for whatever reason, let's say we turn the temperature, let's say we give everybody a hot cup of soup, right? And momentarily everybody's core temperature goes up because they drank a hot cup of soup, right? Then we're going to have a skew that goes to the high side of temperature. It's not going to escape 38.5, right? But it's going to all the values are going to go up briefly for that moment in time, right? And so then we won't necessarily have a normally distributed population, depending on how everybody responds to that hot cup of soup. Now, if everybody responds the same way, exactly the same way, then all we're going to get is a normal distribution curve shift, right? But if everybody behaves not the same way, then we're going to get skew. Make sense?
Yeah.
Okay. Kurtosis is fairly useless. I'm not sure why you would necessarily even use it. I hardly ever do. I'm sure there's a statistician out there who, if they were to see this, they would freak out at me. But so if we draw our little friend, the bell curve, right? So kurtosis refers. What's that?
You're just the Bob Ross of statistics.
That's right. Yeah, we just need a little bit of cloud here. Yeah. So if we, so kurtosis basically refers to how sharp the curve looks at the top, right? So something that has high kurtosis is going to look more like this. And something that has low kurtosis is going to look a little bit more like this. So in some ways, it gives you a little bit of an indication of normality, which is basically what they're trying to get at when they say the kurtosis and skew are normal, or not excessive, or whatever it is they've decided to call it, right? But what it does is it basically tells you whether or not you have a normal distribution or not. Because if you have something that has a high kurtosis, then what's going to happen here is that you're not, this is where that standard deviation comes into play, where normally you have your 66%. If you have a higher peak, then what's going to happen is that your standard deviation is going to look shorter, because you have a higher, it's not going to take as long to get out to 66% on either side of that.
Okay.
Right. So that's all that means. And so that's just another way of checking whether or not your number, whether or not your distribution was normal or not. Right. And I think there are some statisticians that still like using skew and kurtosis indices. I think a lot of statisticians are like, look at the curve. Does it look normal? Okay, fine. Like, don't spend too much time worrying about, how robustly normal your data is, provided you have the experience and the knowledge to do that, right? And so that, I think ultimately that's what it comes down to, rather than, depending on hard numbers. Because if you put 100 statisticians in a room, there's probably at least 7 different interpretations of what's an acceptable kurtosis to be normal and what's an acceptable skew to be still considered normal, right? It's kind of like when people do t-tests on data that shouldn't have t-tests done on them, and they've done these papers where they've been like, well, how bad is it if you use this inappropriately? And it turns out it's not actually that bad, right? You still shouldn't do it, but if it happens, then it doesn't like totally, screw over the whole experiment kind of idea. So I think, that's partly why they have these debates, and why so when somebody says that skew and kurtosis is normal, or how did they phrase it? They put it, yeah, and demonstrated normal distribution, right? So like, we don't know, we have no idea what that actually means. We just know that they did the measurements, and probably SPSS, which is the worst statistical package in the world in my hands, in my view, mostly because I think it just automates things so much that you don't actually need to know what you're doing. And it will spit out information at you that you can literally like put into quotations here, right? Where you're just like, okay, I'm just going to write this because that's what SPSS told me to write. And you can, as a peer reviewer, you can usually spot that from a mile away because it looks like a computer generated that text, right? Yeah. And all that really says is that they used SPSS, and SPSS told them, well, you seem to meet these criteria, and they don't actually know what those criteria mean and what the limitations of that criteria are, right? And so, I don't know that it's definitely not a normal practice to always look at your skew and kurtosis indices. Like, if you look at a curve, you can squint, you kind of squint at it and it's like, oh yeah, that looks totally skewed, right? And then when you calculate your mean, median, and mode, it really looks off. Like that's really, that's a far more valuable tool than any of this other crap, right? So yeah. If your mean and your median don't agree, then you really have to start squinting hard at that curve, because something is probably not quite right. Regardless of what your distribution is, right? So that's what skew and kurtosis basically comes down to. I don't think it's worth spending like more time than that than we have already spent on it. But you know, the concepts are important. I think skew is a really important concept to get, but not an important concept to test for, right? So you know, you should be able to recognize if a population looks skew. And
curve.
Hello, Mr. Hartman.
Hey, Bill.
Hi, Bill.
And so if you don't understand skew, then you're not going to recognize it, right? That's all. That's what it comes down to. All right. All right. Where are we going next? Let me look at our list here. I'm sure there's an easier way of doing this. Okay. All right. Z-score. I say Z-score. I know you guys say Z-score. It sounds super weird when you guys say Z-score. I'm sorry.
Z-score. I sound more sophisticated like that anyway.
Yeah. Yeah. So Z-score appears right here in the text. So this is a good time to do it. So there's Z-score or Z-score. Oh, damn it. I'm going to like totally kill myself over this. All right. So let's go over this concept here. Oh, no, that's not what I wanted to do at all. All right, there we go. Plus, insert a page, plain paper. All right, so a Z-score or a Z-score ties in well for the fact that we've actually already discussed normal distribution, because a Z-score or a Z-score only has context within a normal distribution. Okay, so again, if you don't have a normal distribution, you can't calculate, or you shouldn't calculate a Z-score, because you're going to get the wrong answer. It's going to look effed up at the end of the day. You'll be like, oh, these don't make sense, and that'll be why, because you're not supposed to do that. So very familiar curve. All right, and there's our halfway mark. Okay, so basically, a Z-score is a standardized way to measure how far away you are from the mean of your distribution. Okay, so what it is it's basically the value of, let me just confirm this before I like tell you the wrong thing. Z-score. See, I don't memorize this stuff either. All right. Yeah. All right. So what it is basically it's the number of standard deviations that that any particular data point is from the mean. So we know that 66% of all our values lie within one standard distribution. That's a horrible way of doing it. All right. Sorry. All right, so if that's one standard distribution, then that is 66%. Okay, that whole thing. All right. And so because you have this information, because you know that 66% exists and that 95% exists within two, then what you can do is you can actually calculate, so this point right here, or rather this point right here, right, it's not quite one standard deviation from the mean. It's kind of like 0.8 standard deviations from the mean, right? And this one over here is, you know, it's more than one. It's not quite two. It's like 1.5 standard deviations away, right? So you're just using standard deviation as your yardstick. Right. And so the Z-score for this point right here is 0.8. And the z-score for this point right here is 1.5. That's all it is.
Awesome. Thanks, bro.
All right. And the way that you calculate that, you know, is there's a formula for it, but it assumes that you are working under a normal distribution or something that's not very far away from a normal distribution. So this is where the skew comes into play, where, you know, if you have this, where this is a problem, right? Because your standard deviation has no meaning in this curve. And so if you calculate a z-score or a z-score, sorry, I'm going to do that all the way through this part. You know, so if you're like, well, how far away is this from, you know, we said the mean is probably somewhere around here, right? Well, this has we have no way of using that unit of measurement, right? Because on this side of the curve, your standard deviation is probably like this big. And on this side of the curve, your standard deviation is probably about this big.
So Brian,
yes.
from that, would you adjust the skew first, then use a z-score? Is there another different score we'd use under that skewness?
So it depends on what it is that you're trying to accomplish by calculating a z-score, right? Okay. And so, yeah, if you need to do it for whatever reason, then you might have to correct your skew. And there are ways of normalizing non-normal data by transforming your data, usually by like doing the square of it or the square root of it. You can try. A lot of the times it won't work, or sometimes it just doesn't work. And you just have to figure out a different way to standardize your data. Okay. What a z-score does for you is it allows you to compare different populations that have different standard deviations, right? Because, you know, one team, like, you know, I mean, this is a bit of a cluster study with this one, right? They have a bunch of different teams. They all have different training volumes. They all have different times and distances, but they still should be roughly comparable when you look at the distribution of their training loads. And so their standard deviation becomes the yardstick by which you can compare the different teams to one another, or people from different teams to one another, right? Okay. And even within a team, there's going to be a lot of variation because of the position that you play in rugby, right? Because that is going to determine, like if you're the goalkeeper, you're not running at all, right? So, you know, that is going to be an issue for comparison. And, you know, frankly, if that's the issue, then you should probably be analyzing your goalkeepers completely separately, right? Because you need to be within some sort of feasible range of values, where 0 is not a great range, even on GPS. Like, it's probably close to 0, right?
So is that why they were saying, I believe there's a portion of it, it was saying that it almost negated the very low acute workloads? I'm trying to remember exactly where on the paper.
Yeah, it's right. I think it's right here. Training weeks in which players performed a chronic workload before a z-score of -2 were removed from the analysis.
Okay.
Right. And that's because, so remember that we said 66% of all your data lies within one standard deviation, right? And 95% of your data lies within 2 standard deviations, roughly 95%. There's a decimal in there, all right? So that means that if you have a z-score of less than 2, then you are more than 2 standard deviations away from the mean, right? Fine. So, and a z-score has the sign because you can be on either side of the mean. If you're up high, that's why they say -2, right? So technically on this diagram here, this should be a z-score of minus 1.5.
Gotcha.
Okay, not 1.5. And this is a positive 0.8. So basically, if your training load was less than 95% of all the values of training load, then they took that player out of the analysis. And so they said 3.8% of the data set was that number of people that were excluded, which is roughly about right, because if it's normally distributed, then 3.8 is, you know, is not too far away from 2.5, which is about the right number of people that should be excluded.
Okay.
Right? Because if it's 3.8 on the low side, then it should be roughly 3.8 on the high side, right? And so this is just a confirmation that, yeah, it's probably normally distributed.
Okay, gotcha.
Okay. It's not like, so it's not totally precise, but it's close enough. Right. And this is where the art of statistics comes into play, because, you know, how do you say, oh, that's close enough, right? You know, and that's it. Stats are not a science. Like, it's totally an art. It's, you know, the math is math, but like the actual application of statistics is a complete art. It's not that scientific. There's a lot of eyeballing.
Yeah.
All right. Okay. Any questions so far?
Nope.
Okay. 1,000. Keep going.
All right. So, Bill, I just wanted to check in with you there. So these are, we started basically just by making a list of concepts or words or ideas where they just didn't seem to make any sense. Do you have anything that you would like to add to this list? No. Perfect. Okay. All right. So let's talk about, I think the next thing to probably draw out of this is a little bit of this relative risk deal. So like this guy right here, I think he comes up right here. So the risk of injury plus or minus 90% CI, which stands for confidence interval. Okay. And then that comes into your relative risk over here. I probably should use a different color right here, right? Because that's how they're reporting. This is basically the report of this. Okay. So if you talk about it now, then it'll hopefully make a little bit more sense later. I'm not sure totally why it's divided by 2. Oh, I wonder if they're actually just, no. Oh, here it is.
2-week interval.
Sorry, I just shut that down. Sorry, what's that?
Is it because it was calculated over 2 different weeks and they were comparing weeks that they're dividing it by 2?
No, hold on a second. It's right here. So, so the reason why they're doing, so normally you don't divide your confidence interval relative risk. So apparently owing to the inability of relative risk to provide plus minus 90% CI, the square root of the upper provided this other thing. This still makes no sense. Relative risk. Oh, I think I know what they're doing. Okay. Wow, that is convoluted. All right. So, all right, let's talk about, do you guys know what a confidence interval is, first of all? I have to reshare this. Hold on a second.
Hey, Brian, by the way, I'm sorry to dip out a little early. I got to leave in 10 minutes for a lunch date in San Mateo.
Oh, yeah. No, I'm going to probably pull this to a close in about 5. So we'll maybe just have enough time to talk about confidence intervals, and then we'll have to come back to the stuff that we didn't cover. Like, there's because of the way that this is structured, it's just important that these concepts are well understood. And so if we're spending like 15 minutes here and there on these little tiny concepts within the realm of the paper, then that's a better use of your time, I feel, than trying to get through a whole paper in one session without really understanding what half the words are. Like we haven't even, we've gone through 1 and 2 so far, right? And so this might take us a few sessions to get through what I think are actually 7 super important concepts for reading papers in general, right? And then as we move forward, the list is going to still probably stay the same size, but it's going to be more advanced concepts, right? And so then we just keep building and building and building using papers that have words that just don't make any sense to anybody.
Until we hit critical mass. I gotcha.
Yeah, exactly, right? At some point you're going to hit critical mass where you're like, oh, all these words make sense and I can actually read this thing, right? And then you can start tearing it apart at that point, right? But until then, we can't really tear it apart because all of these words are foreign, right? And so there's no point in even criticizing the paper because we need to understand these concepts before we can even go towards that, right?
Yeah.
Okay, so let's briefly go through confidence